So as we covered earlier, there is no direct access to SPU, to main memory. SPUs cannot directly address main memory, it's via DMAs only. When aliasing is set up, then yes, whatever SPE's local store is being aliased into the effective address space, that SPE will do the address translation. But normally by default, there's no address translation, there's no visibility to main storage apart from DMA accesses. Again, another diagram to show the access methods. The blue lines over here, the blue lines indicate the DMA transfer paths between the SPE to another SPE or to a PPE, and access channels between the SPU and the local store, which is a 16-byte load and stores, and then from the local store to the from basically an SPE, also the SPE can talk to the IO, any memory mapped IO devices also. Coherence and synchronization, all transfers between the local store and the main storage are coherent, and it's a necessary feature if you think about this architecture, because there's 8 processing elements, all of them are mapped into the effective address space, anyone can write into main memory. So obviously there was a need for hardware enforced coherence protocol. So whenever there is a load at a particular request, all the cached copies for data residing at that address are checked, and if there is any touched cache copy existing, first that value is written into the main memory and then the load is completed. Basically a snoop mechanism. Each DMA command is tagged with a 5-bit tag ID. It's basically just an identifier to identify one particular DMA transfer. So all SPEs can initiate DMA transfers. The PPE can also initiate DMA transfers. However, the DMAs from SPEs only are recommended. There's a few reasons for that. Basically, there's more SPEs, and the command queue on the SPE side is bigger, 16 entries versus 8 entries for the PPE command queue. Also, there's only one PPE dealing with everything, controlling tasks, switching, everything, right? Save, if there's any context, save and restore that needs to be done, it's the only entity. So why load the PPE again with another task of initiating DMA? Another theory that we have is consumer initiated requests are more manageable. So SPE, being the consumer of data, always should be initiating the DMA transfers. They are more effective. The peak bandwidth is higher when the DMAs are initiated by the SPEs, when the transfer size is a multiple of 128 bytes, because they generate full cache line requests. And the address offset in the main memory and the local store address offset both need to be a multiple, basically multiple of 128 bytes. So in other words, we're not generating any partial cache line requests. All cache lines are 128 bytes. So that's the reasoning behind it. And these are the registers on the PPE. There's different registers to handle floating point computations versus fixed point. There's a condition register, typical register format, like in an Intel architecture. The PowerPC instruction sets, all instructions are 4 bytes long, and they're all aligned on word boundaries. It supports byte, half word, word, and double word accesses to all the general purpose registers, and supports word and double word operand accesses between a storage and a set of floating point registers. Signed integers are always represented in 2's complement form, and there is an extensive vector or multimedia instruction set. So in other words, you can write vector code on the PPU also. However, what we really recommend is just to do all the vector computations, because essentially when you're doing vector, you're trying to write some effective high performance code. So you would want to do that on SPEs because they are more adept at handling compute intensive code. Again, these are the instruction types for reference. So there is cache control instructions available, flow control instructions available, general load and store instructions, memory synchronization instructions, typical to a PowerPC architecture. Some more user mode instructions. Again, the processing units in the PPU, the FXU fixed point unit, the floating point unit, the vector unit. there's some more instruction types. There is all these, basically the point of all this information is that there is support for all these instructions available. So your application could be anything. It could be an algorithm from the A&D space, or from electronic design and automation, or seismic, or image processing. And it can be any application, and so the instruction set is capable of handling a diverse range of applications. The message we are continuously trying to send by doing all these workshops and contests and these ecosystem related activities, to send that cell is not just a PS3 or a gaming chip. When it was designed, the architects had it in their mind that it has to take technology and high performance computing to a totally different level by doing some kind of breakthrough design and beating the competition that we face from all these SMP architectures or other multi-core architectures. So again, when you design this kind of breakthrough technology, obviously the programming will not be as similar or common to the mainstream programming. So that's why the need for this different kind of programming and DMAs and synchronization. So it takes a step more of effort to get the performance out of this hardware. PP has got its own C, C++ language extensions, vector data types. They're all, even on PPE, the vector data type is 128 bits, 16 bytes. So it can hold 16 8-bit values, signed or unsigned, 8 16-bit values, 4 32-bit values, and 4 single precision IEEE floating point values. And there's 3 categories of intrinsics. Intrinsics is just instructions like the VMX instructions. Specific instructions have a one-to-one mapping with a single assembly language instruction. Generic, they can map to one or more. Predicates, there is some conditional kind of instructions that are called predicate instructions. Basically, they'll compare 2 values and generate a mask. And that mask will be used directly as a value to detect a condition or a branch. And this is how a VMX program would look like. The top part of this program just defines a union consisting of an integer array, or 4 elements, and then there's a vector unsigned, vector signed int, and then type def it to vec_var. So the main program is initializing a vector. So this is how you would initialize a vector. So vconst is a type of structure vvar, a vec_var, and vconst at myvec would be initialized to 4 floating point values, 2 2 2 2. v1 is another vector of type that union that we just defined, and load it, initialize it with different values, and then do a vec_add. So that vec_add is called a vector instruction or a VMX intrinsic. So basically, with one instruction in one cycle, we're doing 4 additions. So which is the whole premise of data level parallelism, or single instruction multiple data. So with one single instruction, you're operating on 4 vector elements. So the result is stored in myvec, and you can print it out the way it's showed in this program. So SPE registers is pretty much simpler than the PPE register model. 128 registers, they all look the same, unified registers. So the same registers are used to do floating point or fixed point arithmetic. So SPE executes both single precision and double precision floating point operations, and single precision, they would be performed in a 4-way SIMD fashion, just like a unsigned int or int. They're all fully pipelined. Double precision operations, however, are partially pipelined. So this morning, Duke covered the even and odd pipelines, where you can run 2 instructions in one clock cycle. One is an even pipeline, like a arithmetic pipeline, and the other one is for memory operations, right? So with double precision operation instructions, though, it cannot be run with any other instruction at the same time. So dual issue is not possible. Apart from that fact, once you execute a double precision instruction, for the next 6 cycles, you cannot execute any instructions of any other type. So there is a 13 cycle clock latency, 7 cycles to perform the double precision operation, and then 6 as a latency. So double precision right now on the current cell BE hardware is a little expensive, or it's not as good as single precision, but it's still pretty good by par. at par with other architectures. Only one rounding mode is supported, it is all round towards 0. Denormal operands are treated as 0. There is no support for infinity, there is no infinity or not a number. And just as I mentioned, no other instructions are dual issued with double precision instructions. There are 13 clock cycle latencies, and only the final 7 cycles are pipelined. And then after you execute a double precision instruction, you cannot execute anything else for 6 cycles. The SPU local store holds instructions and data. So in the 256 kilobytes of memory that you have to fit the code and the data sections. The instruction prefetch will at least deliver 17 instructions, because the DMA, every DMA operation happens once in 8 cycles. So in other words, for DMA read it's 1 by 16th, and for a write it's 1 by 16th. So it doesn't really impact the usage of the single ported memory per se. And because there's only there's only one port for reads and writes, so there's 3 different kinds of operations that have to go through that local store. DMA read and write, SPU load and store operations, and then instruction prefetch. The priority, however, the highest priority goes to DMA reads and writes, and then loads and stores, and then instruction prefetch. The reason why the loads and stores have a higher priority over instruction prefetch is because the load and store will at least help you with the program execution. It will take the program go further. Instruction prefetch, on the other hand, is speculative, right, most times. So even pipeline by 0 and our pipeline, all the instructions, there's a programmer's handbook in the microelectronics website. Fully, it covers everything from architecture to coding standards to optimization mechanisms to thermal and power monitoring to performance counters to virtual storage, everything, decrementers, hardware clocks, everything is covered in the handbook. A good part of the handbook also goes over the instructions and their clock cycle latencies and which pipeline they are issued in. All the data is big Endian on the PPU and SPU, and which means the MSB would be 0 and the LSB would be the bit 128 or 127. Again, SPU instruction data type, the names look the same, it's always vector following the data type. There's about 204 instructions, shift and rotate instructions. There is no rotate right. So when you have to rotate left, you just give it a negative index to do a rotate right. The synchronization and ordering instructions. And again, even in the SPU language extensions, there is 3 classes, specific, generic, and composite. The third category is different. Third category is composite, which means it's basically a sequence of 2 or more specific or generic instructions. Specific is directly related to assembly level instruction, and generic is basically 1 or more assembly level. The examples are also given. Any specific instruction will be proceeding with an SI underscore, and a generic would always be a SPU underscore, add, subtract, multiply, everything. And this is how this data is stored in memory. The first 4 bytes are called the preferred slot. So in other words, we highly discourage the use of scalar data types on the SPUs. Right? We say just use vector because that's the way you will optimally use all the resources available to you. So if you have to use scalar data types, always make sure that the data always resides in the preferred slot, the first 4 bytes. So that when there is, for example, I think in the third presentation we go over the SIMD operations, but basically it helps with the alignment, it's less overhead for the compiler, it's just better in terms of execution. So in other words, this is the byte, let's see, this is one vector consisting of 16 bytes which can store 4 integers or 4 floating points or 2 double words consisting of 8 bytes each or 1 quad word. This is a typical example of instruction. SPU underscore insert will insert a scalar into the vector D. SPU promote will try to promote one scalar to a vector, and then extract by, you can give it an index. Going back, this is all, if say we're dealing with 4 unsigned int in one vector, right? So 0 through 4 would be integer element 0, or you can call it integer element 1, 0 through 3, and then 4 through 7 would be integer element 2. So sometimes you might need to extract integer element 2 or integer element 3 from one vector and print it. So you can do that via this instruction spu_extract. And there's a whole bunch of instructions like this. And all loads and stores are 1 quad word at a time, 16 bytes at a time. There is built-in compiler directives. The built-in expect is used for branch prediction. Remember, SPU does not have any hardware support for branch prediction. So we try to keep the SPU hardware as simple as possible. Less silicon, less heat, less complication. Enforcing the 16-byte loads and stores, it removes the necessity to deal with exceptions or traps. So and the way we enforce that okay, all data types are aligned on 16-byte boundaries is when you define a float factor, use this macro, aligned of 16 would align it for efficient data transfer. And you can always say, do a branch hint by using align_hint. And this is an example of an SPU program. So similar to the other example that we saw, this is the union with consisting of 4 integer values and 1 vector signed int, and 3 vectors defined, and then initialize the first vector with 4 values, initialize the second vector with 4 values, and now to add it, it's instead of vec_add, the SPU would do SPU_add. So there is a local store with the SPU processing unit, and this is the memory flow controller. The memory flow controller consists of a DMA queue where you can queue in the DMA requests, a DMA engine, basically it's a DMA controller, atomic facility for any instructions that go through MMU, and RMT is replacement management table, and then there's memory mapped IO registers to be read and written into by the PPE. And MFC commands. So the memory flow controller is this whole and sole entity responsible for all communication with any other devices, right? So on the SPs. So the purpose of MFC commands is to basically access main storage. 2 main initiatives, right? May access main storage, and then to maintain synchronization with other processors and devices in the system. Now they can be issued either SPU or by the PPE, right? Basically the instructions are going through the MFC, they can either be issued by the SPE or by the PPE. And all these instructions are basically channel instructions. So anytime you're trying to do a read or a write, basically it's a read or write to the channel instructions. For the PPE though, it's always memory mapped IO instructions. So as we covered in the previous diagram, whenever the SPE needs to talk to basically the DMA engine, if you see the red line is the data bus. It's for whenever the SPU needs to talk to communicate with the MFC, it uses channel instructions, and whenever the outside entity, the PPE is existing somewhere here, it needs to talk to this MFC, it uses this memory mapped IO instructions. And then all MFC commands are queued under MFC SPU command queue. The proxy command queue are for the PPE initiated memory mapped IO instructions. And this is some detail for your reference. So all operations on any given channels are strictly unidirectional. They're just message passing interfaces, basically. They're always done in program order, and you can always query the status of a channel instruction by doing reads and writes. So again, whenever we're talking about any DMA requests or any mailbox communication or synchronization commands, the reference point is always the SPE. So when we say get, it's into the SPE, and put is out of the SPE. The internal instruction for a DMA command is SPU write channel. Basically, it's a channel instruction. Composite intrinsic we just covered is a collection of one or more specific or generic intrinsic, right? FC DMA 32 is the composite intrinsic, but the instruction that we use is a wrapper external. It's a much simpler wrapper routine. Is MFC get. This is the command that we will most commonly use in all the code, and these are all defined in SPU_MFCIO.h. This is a syntax for MFC get. It's a simple DMA transfer command. Basically, you give the offset, the local store pointer, as to where you want to put the memory in once you fetch it from the main memory, and where do you want to fetch the memory from, that is the effective address in the main memory space, and then how many bytes, and then assign a tag, an identifier to the memory, so that if you want, once you initiate the DMA request, you want to query if it's done or not. So the tag ID can be used to query the status of a particular DMA transfer. And then transfer class ID, TID, is used when you want to change or manipulate the transfer mechanism on the bus for it. Usually it's just default. I'm not sure if it's enabled in the current SDK development too. RID is replacement class ID. Again, this is something that we use when we're using software managed cache. There's features for fences and barriers, like a typical Linux OS supported fence and barrier. Nothing different over here. It's just that now we have combined that fence and barrier feature with the DMA command, so we have more control over I/O. There's a 5-bit DMA tag for all DMA commands. Again, so up to 32 tags is what we can create. This is an example for a fence and barrier. So essentially, barrier is something, say for example, this is a green slot, that is a barrier, that is a DMA transfer that you have issued with a barrier option. So any preceding DMA transfers cannot be executed until this barrier instruction is done, and even succeeding DMA commands cannot be executed until this barrier instruction is executed, versus a fence, which only stops all the preceding DMA operations to be done before this particular DMA transfer is finished, but any succeeding ones, any DMA issues that are issued after this fenced command can just happen fine. So that's the difference between the fence and, it's like a typical fence and barrier. Transfer sizes always have to be 1, 2, 4, 8 or multiple of 16 bytes for DMA. Maximum is 16 kilobytes per DMA transfer. 128 by kilobyte alignment is preferable to get optimum performance. The command queues are 16 element for SPU initiated requests. For PPU, it's 8 element queue. There is something called DMA List, which is a very excellent feature again that's provided on the SPEs and on the cell broadband engine. It's basically a scatter gather mechanism, so by which you can get the SPE can initiate a DMA list. In a DMA list, what it tells is that asynchronously get memory from wherever it's available in the PPE address space, in the effective address space, and that happens asynchronously while the program is executing on the previously fetched data, previously retrieved data. The advantage to the DMA list is that it's a kind of a solution to fragmentation in the effective address space. It will just grab wherever it is there and maintain it in a list and just do it, process the whole data asynchronously while the execution is going on the previously issued data. It can contain up to 2K transfer requests, and each transfer request can be up to 16 kilobytes. So on a total, it can fetch 32 megabytes of data. That's the API MFC get. That's a simpler API where you just specify the local store, actually the same API, local store address, the effective address, the size, and usually these two fields are zeros. You can check the status of a DMA command by MFC by this command, the read tag status. And this is the API, MFC write tag mask is the API to set the tag mask. Basically, a tag status bit of 1 will indicate that no DMA requests tagged with that specific ID are still in progress. So basically, it has completed. So you can either check you can create multiple DMA requests with the same tag ID. So in a way, you're grouping them in one category. So sometimes you want to make sure that all this bunch of DMAs all can be collectively addressed with one. It's like basically creating threads in one thread group. Similarly, doing all DMA transfer requests under one tag ID. So you can query on that tag ID to check if all DMA requests are done. So you can check on status of one tag or all tags, all DMA requests are done or not. So it's a typical example of DMA memory to local store. So MFC get operation, define the tag mask, and then do an MFC get operation. So it basically reads the contents from mem underscore address in the effective address space and puts it in the address pointed by ls underscore addr, and then you check the status, then make sure it's wait for all the DMA operation to be done. So that was the get, and this is the put. When you're done with the computation on the SPE side, you can use this instruction, the MFC underscore put instruction, to write it back to the main memory. And how do you transfer data between SPE and SPE? The other SPE doesn't know what the other SPE's address is. The way you can do it is that PPE, however, knows all the SPE's IDs, right, and the address offsets. So what one SPE, say I'm SPU2 and I want to send data over to SPU4. So there's no point sending the data over to the PPU and then PPU sending it over to the SPU4. Instead, what the SPU can do is via mailbox or some other mechanism, try to get the local store address for SPU4. So once you have the local store address for SPU4, using the same API over here. So instead of the memory address, you will give the local store address of the other SPU and then put it back in your own SPU address space. And tips to achieve peak bandwidth: always quad word offset aligned data requests. They always have to be aligned 16-byte boundary. Mailboxes, they are always 32 bits in length. Basically, the mailboxes are a really neat feature, really lightweight mechanism to say query status, send error code, return codes for program completion, some kind of message to say, okay, I'm done, you start, or there's an error, or wait, something is wrong, something like that. So any kind of messages you can send via mailbox, 32-bit messages. So the PPE mailbox queue is one deep. There is a SPE write outbound mailbox queue for all the messages that it wants to write out to the PPE. There's a write outbound interrupt mailbox queue, the same thing, except that after the data is written, it will generate an interrupt. And then SPU read inbound mailbox queue, basically PPE would write to it, so any messages that the PPE wants to send, and then the SPE can read, and it is 4 deep, in other words 16 bytes. So 4 32-bit messages, 16 byte wide. This is the way the PPE, again, even for mailbox, it has to interact with the MMIO registers. So this is the API, pretty straightforward, really simple read write API. So this is the MFC PPE mailbox, right? One PPE mailbox is there, one PPE interrupt mailbox is there, and then SPE mailbox is there. So anytime SPE wants to say read out from the mailbox what the PPE has written for it, it can do a read out mailbox. All the SPE reads and writes to mailboxes are blocking. So in other words, if SPE is trying to write to the outbound mailbox that is already full, it will halt. It will stall basically. So it's always a good idea to check the status, to read the channel count and see if there's any data already there in the mailbox, if it's already full. If it's full, then you wait. Also, if SPE is trying to read from an empty mailbox, it will also stall until PPE writes something out of it, write something into it. So in order to avoid these stalls from the for the SPE, it's always a good idea to read the mailbox count and see if it's not empty or if it's not full. Versus the PPE, if PPE is trying to write to the mailbox which is already full, it will just overwrite the last entry, which is again not a good thing. So it won't halt the PPE, because halting the PPE or stalling the PPE is a bad idea, right? That's your main application is running over there. So you want to check the status and make sure you don't overwrite data. So again, this is just the API description. If the outbound mailbox is full, the channel count would be 0. So if the SPE is trying to write to a full mailbox, it will remain stalled until PPE will read the message. So there is one 32-bit entry which is vacant. So there's room for write. And when the mailbox is read through the memory mapped IO address by the PPE, the channel count is incremented. Similarly, with write outbound interrupt mailbox, it's the same as the write outbound mailbox, except that when the write is done, an interrupt is raised. So provided the interrupt is enabled, So first the interrupt is serviced, and then PP goes and reads the MMIO register to get the data value out of it. So to avoid the SPU stall, always read it before writing or reading, at least for the SPU. And for the PPU, if you don't want to read stale data or overwritten data, make sure you check the status. Similarly, for read inbound mailbox channel, it will stall on an empty mailbox. So when the SPU wants to read any message that is waiting for it in the inbound mailbox from the PPE, make sure you read it, make sure it's not empty, because if SPE tries to read on an empty inbound mailbox, it will stall until PPE writes something to it. Okay, so this is the way to create the thread. So when the PPE would try to create a thread, this is how it will try to create a thread. SPE create thread ID. This is the group, thread group. If you have created a thread group before creating this API, you'll pass that in. And then this is the pointer for the program, and then Duke is going to cover that hands-on in the lab to see the code and see how the SPE program. Basically, this SPU load image has to be the same name that is defined in the SPU makefile under the program_SPU. So it becomes a global reference. Again, to check the status of a mailbox, the simple API, stat out mbox, pass it the SPE ID, find out if there's any data. Write out interrupt mailbox is also the same. Now, when the PPE is trying to call it, it will pass in the SPE ID. When the SPE is trying to call it, obviously there's no SPE ID. All it needs to try to do is, when it's trying to do the write, it just sends the data to the PPE. So in the lab, there will be an example program. Very, very simple. Our premise is to basically get the message over to you on the basic mechanism on how the transfer happens and how the APIs need to be used, and we hope that you'll just build on top of it. Obviously, in real world, it won't be as simple as this. It will be much more complicated, but if we set the right ground, we can be sure that the real application development can happen easier. Okay, so again, we just saw this in the previous presentation. Reading into the local store is using the MFC get operation. So example 1, there will be a getBuff.c when we are covering all these examples. All it does is basically it will write an SPU program that will transfer the data into an SPU buffer from a PPU. So from the effective address space, using the MFC get operation, it will write the data buffer, and then it will try to get the data into the SPU, and then write the data in the buffer to verify the transfer, basically just print it. So this is how the PP program would look like. Do all the defines. The libsp is a libsp runtime management library, and then just standard header files. Right now, one thing that I want everyone to notice is in the PPU program, always you'll have to define one variable for SPE ID. This is the buffer that we are creating. The malloc call won't be a standard malloc call. It would be malloc_align. So in this case, and again this definition, the support for this is there in the libmis.h header file. So malloc_align is saying create 128 bytes and then align it on a 128 byte boundary, 2 power 7. So the 7 is an argument which does log 2 of the input data. So in this buffer, we're writing the data, good morning, and then creating the thread. So in this case, we have not created the thread under a group. So the first parameter is a 0. And then getBuff_SPU is the program handle for the SPU program. And we'll be seeing that right now. Makefile will look like this. The base level makefile. The directory would be SPU, and then program PPU would be having this name. And then the if you notice in the imports directory, you're linking to the SPE runtime library, the MISC library for all the memory operations, and then put buff_SPU, which is the same as the parameter over, I think it's incorrect over here. It has to be getBuff. So this name would be the same name as the program handle over here. And this will be created over here, extern SPE program handle getBuff_SPU. So essentially in the PPU symbol space, this program handle, whatever is the SPU references will be visible to the PPU because it's embedded in the PPU executable itself. And this is the smartest way we could come up with in order to entertain the two different architectures inside only one binary. Also to save any things like inter-process calls. We don't need any IPCs, we don't need any messaging mechanisms. We want to keep it simple so that they are still visible in the global address space, and we don't need any explicit commands so that the SPU symbols are visible to PPU and vice versa. So getBuff SPU would be the program handle or a reference to the executable, the SPU executable. The buffer there is a second parameter in the SP create thread, which is like the environment pointer, which would be sending over data if you wanted to over to the SPU code. So this is like we want to say, okay, I've created a thread and this is what I want the thread to do, because the getBuff_SP is not just a program handle, right? It's a program which gives a defined role for the thread. Like you can create the thread, but what is the thread going to do? What is its code portion? The handle gives it, by creating the thread, you're actually giving the code portion to it.